In this video, I'm going to go through the solutions for each of the problems on our review for Exam 3 in trigonometry. Remember, Exam 3 is covering how we solve triangles and find their areas, so applications of trigonometry to triangles. On problem 1, we know that A is equal to 2. We know that capital A, which is the angle across from little a, is 40 degrees. And we know that C, so actually that's all we know. We know the last angle, capital C, is actually a right angle right here. So I'm going to start by finding the first angle, which is the easiest part of this, because B is going to be 180 degrees minus the 40 degrees minus the 90 degrees, the two angles that we know. 180 minus 40 minus 90 leaves us with 50 degrees. Okay, now that we know that this is 50 degrees, we can use either 40 or 50 degrees to find the remaining two sides using known trig functions. So I'm going to take advantage of the fact that I know, and I'll circle these in green, I know this, but I don't know this, and the relationship of those three sides is sine, because the a equals 2 is opposite the 40 degrees. So sine of 40 degrees is 2 over c. So if I move the c to the left-hand side, I get c times sine of 40 degrees equals 2. So c would be 2 over sine of 40 degrees, which I place into my calculator, and I get 3.11. Notice the instructions tell us to go to 2 decimal places, so that's my little c. I can find my remaining side, b, by either the Pythagorean Theorem or using now cosine of 40 degrees is... actually, I tell you what, I would prefer, while there's multiple ways to do this, I would like to use values that aren't approximated. So I still know this, I'm going to do this in yellow this time, this 40, this 2, and this b have a trig function that relate them. In fact, that's tangent, because it's you can write tangent as opposite over adjacent. So tangent of 40 degrees is equal to 2 over b, because 2 is opposite to 40, right? 2 is opposite over the adjacent side, 2 over b. Okay, so that b I move over, so I get b tangent of 40 degrees equals 2 by multiplying b across, and then dividing by tangent of 40, 2 over tangent of 40 degrees. Plug that into my calculator, and I get 2.38 for b. And that's problem 1. Now moving on to problem 2. We've got a triangle that is, we're going to assume it's right, because again, you read the instructions to solve the right triangle. So I'm going to draw it arbitrarily here. Let's just pick a right triangle here. Let's call this side down here little a, so that's 4, which makes this angle up here capital A. C, which is the hypotenuse, is 9. B we don't know, and capital B we don't know. Okay, so in order to find this triangle, we're going to have to use an inverse trig function, because we don't know one of the two angles. So I'm going to relate the two sides that I know, which is this one and this one, which could either be the adjacent of B or the opposite of A. I'm going to choose the adjacent of B. Cosine of B is equal to 4 over 9, adjacent over hypotenuse. Okay, that means cosine of B is, actually, I can go ahead and go to the next step. I can write this as B is the cosine inverse of 4/9. So plug that into my calculator, which gives me 63.61 degrees, 2 decimal places. Now I can find capital A by doing 180 minus 90 minus 63.61. Again, plugging that into my calculator, and I get 26.39 degrees. The last remaining side is B, So we could use trig functions for this, or we could use the Pythagorean theorem. I'm going to choose the Pythagorean theorem because that's the one that I have that would set up an equation that doesn't use any of these approximated values here, right? I could use one of these trig functions on one of these angles here to relate that to side B, but I would be using rounded values. So the best possible way to do this would be to use Pythagorean theorem, which is that 4 squared plus b squared is equal to 9 squared, or 16 plus b squared equals 81. So subtract 16 from both sides. 81 minus 16 gives me 65, so b squared equals 65, or b is the square root of 65, which is 8.06. And we've solved the two right triangle problems. Okay, moving on to the next one. We've got an application problem that involves right triangles. A straight trail with a uniform inclination of 15 degrees. So we're traveling up at an angle of 15 degrees. Leads from a lodge at an elevation of 600 feet to a mountain at a lake that is 6,100 feet. Okay? So this elevation right here is 600 feet. This elevation up at the top is 6,100 feet, which means we know that this distance right here can be calculated. We want to know how long is this side. What is the length of the trail to the nearest foot? Okay, so first of all, let's find this distance right here. 6,100 minus 600 gives me 5,500 feet. Okay, we know this angle here to be 15 degrees. So what trig function relates 15 degrees to the side opposite to the hypotenuse? The answer is sine. So sine of 15 degrees is opposite 5,500 over the unknown. I'll put an x there for the unknown. And now I'm going to solve this for x. First multiply it to the other side. X sine of 15 degrees equals 5,500. Divide both sides by sine of 15. Sine of 15. And we get x is whatever 5,500 divided by sine of 15 will be. Throw that in my calculator. And I get 22,250. It says round to the nearest foot, so I don't need any decimal. That is the length of the trail. All right, moving on to the next one. We're now going to be looking at some of our oblique triangles, triangles that are not right. In this particular case, notice we are given an angle, and a side, typically referred to as a side angle problem. That's a law of sines. And again, if you can't remember that, it's a matter of just checking to see what you know and how you can set up an equation. I always start with law of sines first, so you look at angles and their opposite side lengths to see whether or not you can, sorry, that was a bad circle, create an equation that has only one unknown in it. Since I've got 25 degrees in 4 and 105 degrees in A, that pair of sides and angles will give me a law of sines equation with only one unknown. I can set it up as sine of 25 over 4. Remember, law of sines takes the ratio of the sine of an angle and its opposite side, and it's constant for all three pairs. So this is going to be sine of 105 over A. Now multiply by cross multiplication, we get that this means that A sine of 25 degrees is 4 sine of 105 degrees. So divide both sides by sine of 25. And A is 4 sine of 105 over sine of 25. Throw that in the calculator. And I get that A is 9.14. Fabulous. Okay, so solving the triangle means I've got to find the rest. I could have done this actually very early on, but capital C is an easy one. That's 180 minus 105 minus 25. Okay, or 180 minus 30, which gives me 50 degrees. So my last unknown is little c, so I can use this new angle that I found here together with the opposite side and pair it up with the b part of the law of sines. So sine of 25 degrees over 4 is sine of 50 degrees over the unknown c. Again, cross multiply. C sine 25 equals 4 sine 50. So c is 4 sine 50 over sine of 25. And from my calculator, I see that that gives me 7.25, and we've solved the triangle. We know little c, we know capital C, and we know a, little a. Alrighty, next one is, we don't have the triangle, so I just draw one. Let's say this side over here is B, so, or this angle, so I'm going to call that 40 degrees. Let's give this one up here C a name 20 degrees. And then A is going to be over here, so opposite that is 2. So we have now an angle side angle case, which is also a law of sines. We know two angles. So what I could have done first last time is go ahead and get my other angle. When I'm given two angles, I can immediately find the third. 180 minus 40 minus 20 is 120 degrees. So I know this one now. But now I've also got to find this little c and this little b over here. And so, again, using my looking for pairs, where I know for two pairs of these, only one unknown. Notice that this pair here has one unknown, this pair has one unknown, this one has no unknown. So if I put that pair with any one of these, I can make an equation with one unknown. I can go sine of 120 over 2 is sine of, say, 20 over c. Of course, I can also do sine of 120 over 2 is sine of 40 over b. Those are the two equations I need to solve. Okay. Hopefully you're getting the hang of this by now. You'll see that after cross multiplying and dividing, we get 2 sine of 20 over sine of 120. Okay, over here you'd get b is 2 sine of 40 over sine of 120. And if I throw both of those into my calculator real quick, I get, let's see, a wrong one. I get a 0.79 and a 1.48. And there are my three solutions here. Boom, boom, and boom. Okay, now the next three problems, as you'll see, all end up involving the ambiguous case. So side-side angle. Let's just draw this first triangle so you can see that that is in fact the case. I've got two sides, so let's say this is A equals 7, this is B equals 9, so this is capital B, 49 degrees, B over here. This is capital A up here, and this is capital C over here with a little c here. So we need to find this angle, this angle. We can't immediately find an angle, so we start by setting up the pair. Let's say this pair with maybe this pair. So that gives me sine of A over 7 equals sine of 49 over 9. Cross multiply. 9 sine of A equals 7 sine of 49. So sine of A is 7 sine of 49 divided by 9. Throwing that part in my calculator gives me a 0.5. I'm going to go several decimal places since I'm going to use this for a calculation. 586,996. So A is going to be the sine inverse of 0.58869. Oh, sorry. 586,996. Or A could be 180 minus sine inverse of 0.586996. Remember, when you take the sine inverse, you have to check both the angle you get from the sine inverse function and 180 minus that angle. So we may have, in fact, two separate triangles that could solve this. So the sine inverse of that number gives me 35.94. degrees. Or A could be 180 minus that, which is negative, sorry, not negative, is 144.06 degrees. Okay? So the next step would be to find angle C. Angle C will be 180 minus the 35.94 I just found, minus the 49 I already knew. So 180 minus 0.94 gives me 140.06 minus 49 gives me 91.06 degrees. Okay? So now that I know that one, I can find my C. Sine of 91.06 over little c would be sine of 49 over 9. Okay, so again, cross multiply and divide, you get that C is 9 sine of 91.06 divided by sine of 49. From my calculator, I get that that's 11.92 units. Okay, so I have solved and obtained one triangle that I know satisfies the problem. Is there a second triangle? Well, let's come down and start this process again. Capital C, if I do 180 minus the 144.06 that I got for A minus the 49 that I know for B, I see that I have a problem. That this gives me negative, accidentally tapped a new slide, gives me negative 13.06, which is not possible. There's only one triangle, and it's this one right here. Okay? All right, so that's the first ambiguous case. Let's try the second one. Boom, boom, boom. We now do, let's say this is 75 degrees, so that's capital B. This is going to be little b, which is 6. Let's do, this is C equals 9, so capital C here and capital A up here, little a down here. Okay, so again, I can do a pair by doing this one and this one with the law of sines. Again, as before, this is side, side, angle. Still law of sines, but still the ambiguous case as well, which means we can get 1, 2, or no solutions. Sine of 75 over 6 equals sine of capital C over 9. So sine of C times 6 is 9 sine of 75. So sine of C is 9 sine of 75 over 6, which in my calculator, 9 sine of 75, and then divided by 6 gives me 1.448889. So C is sine inverse of 1.44889. Now you can throw that in your calculator and see that you get an error, or just recognize that's bigger than 1, which is not possible, which means there's no solution. As soon as you get to that point, if you can't solve for that C, then you're done. No triangle can satisfy those conditions. It's LE, sorry. All right, last one. You can probably guess, but this one's going to be one where we get two different answers. So let's do, here's 27 degrees, gets capital B, so this is 16.2. let's say this is 17.84, so that's capital A up here, and then C and little c. So I can use law of sines here and here. Sine of A over 17.84 equals sine of 27 degrees over 16.2. 16.2 sine of A equals 17.84 sine of 27. All right, and then sine of A is 17.84 sine of 27 divided by, that's 27 degrees, divided by 16.2, 17.84, 27 sine, multiply those, and then 16.2 divide, I get 0.49995. And I take the sine inverse of that, so A is the sine inverse of 0.49995, or 29.996, which gives me 30.00 when I round it, or A could be 180 minus the 30.00, which gives me 150 degrees. So from that point forward, I got two triangles to solve. Capital C will be 180 minus 27 minus 30. 150 minus 27 is 123 degrees. And then let's do, I know this is now 120 in here. Oh, sorry, 123. So I can do a law of sines. Sine of 123 over C is sine of 27 over 16.2. Okay, so C would be 16.2 sine of 123 divided by sine of 27. 16.2, 123 sine, multiply that, 27, take the sine of that, and divide, and I get 29.93. So there's triangle 1. Let's see if I can't get a second triangle now. So I'm going to try the second one. Solve it the same way, 180 minus my 27, which I know, minus the 150 I just got. And in this case, I actually get a number that's not negative. I get 3 degrees. So this will actually have a second triangle. I've got these two angles. So now I can do sine of C, which is 3 degrees, over little c equals sine of 27 over 16.2. Notice all that's changed from this equation that's over here is that instead of having 123, I've got 3. Okay, so 16.2, I'm just going to go ahead and actually solve it all the way for C. C would be 16.2 sine of 3 divided by sine of 27. And throwing that into the calculator, 1.87 is the answer that I get. So here's triangle 1, and here's triangle 2. Both of them satisfy the equation. All right, so last thing, let's do a law of sines application problem. So number 9, we're going to take, draw the situation that we've got. Two surveyors are 180 meters apart on the same side of a river. And they measure their respective angles to a point between them on the other side. Okay, we want to know how far that point is from each surveyor. So 2 answers to this question. So think picture-wise, you've got a river here. You've got a surveyor on the same side as the other surveyor whose distance apart is 180 meters. And somewhere over here between them is a point that they're both measuring to. And they know that the respective angles between them and the other side of the river is 54. So this is 54 degrees, and say this is 68 degrees. We'll call this A and this B. We want to know how long are those sides, line of sight distance. Okay, Notice, we'll circle this in yellow. This one, and this one, which is an angle, side angle problem. Okay? So we can figure out this other angle here, which we do need to know in order to set up a law of sines. We've got to find out what that side is. Let's call that capital C. So C is 180 minus 54 minus 68. So I'm going to my calculator and subtracting both of those from 180, and I get 58 degrees. Okay, sorry, I switched to red there. I'm going to go ahead and do this in blue like I've been doing the rest of these. Now I can say, to get, say, the value of this A here, it's opposite 68. Okay, so I'm going to do sine of 68 over A, and then sine of this 58 degrees here over 180. Sine of 58 over 180 meters is going to be sine of 68 over A. And of course, I could do the same thing with B. Sine of 58 over 180 is sine of 54 over B. That's a B there, right? Because these guys are opposites here. Okay, so just solve those two equations and we got it. So A here would be, I'm going to go ahead and cross multiply and then divide the sine of 58 over. I get 180 sine of 68 over sine of 58. If you don't know what I'm doing right there, go back to problem, the first one of our oblique triangles, and I walked through how I got from here to here. B is going to be sine 180 sine of 54 divided by sine of 58. So this one gives me 196 asks for the nearest 0.1 meters. So I'm going to go one decimal place, 0.8 meters. And this one, from my calculator, I get 171.7 meters. Okay, on the next triangle, we're going to see that this now moves on to one that we need the law of cosines for. So if this is, say, A over here, 70 degrees, which makes this side, we'll say this is B, and this is little b equals 4. This is C equals 5, and this is capital C, we don't know. Then this is a side angle side, which means we need the law of cosines, because this little a over here we don't know. And then we've got to figure out these two angles here separately. So once we get A, we could then use the law of sines or another application of the law of cosines to figure out one of the two angles. I like to do law of cosines twice. If I can avoid using inverse sine at all, I prefer to do that. All right, so remember my anchor notation, where you've got this opposite of these. Okay, the formula then can be based on a pattern that you recognize. A squared would be 4 squared plus 5 squared minus 2 times 4 times 5 times cosine of the angle between them. Okay, it's the opposite. Okay, equals the 2 on either side. So this would be b squared plus c squared minus 2bc cosine of the a, the angle between them. Now that's as simple as plugging into your calculator and taking the square root. So a squared is going to be, this is 20.31919, or a is the square root of that, which is 4.51. Okay. So now what I would do is, let's do this in green. I've got another anchor with an opposite side that I know. Like I've got this side opposite to, I now know this, but I don't know this. But notice this little green anchor has only one unknown, the angle itself. Okay, so I could set this up as 5 squared equals, now a, which I know, 4.51 squared, plus b, which is 4 squared, minus 2 times 4.51 times 4 times cosine of capital C. Okay, so I can move this over here, and then divide this off. Okay, and what that gives me is cosine of c equals 5 squared minus 4.51 squared minus 4 squared divided by a negative 2 times 4.51 times 4. Throwing that in my calculator, this is a 0.3137. So C is cosine inverse of 0.3137, or the angle 71.7 degrees. And then from there I can come back over and do that capital B is 180 minus 70 minus the 71.7. 180 minus 70 minus the 71.7 gives me a 38.3 degrees. And now I've solved an side angle triangle. Excellent. Last one is the last type, last case we haven't considered yet, which is the side. 19, 16, and 11. That makes this A, B, and C. Okay, so again, using any one of my anchors, so let's say this one, and this one, boom, boom. That gives me 16 squared equals 11 squared plus 19 squared minus 2 times 11 times 19 times cosine of B, which is going to give me that cosine of B is 16 squared minus 11 squared minus 19 squared, because I'm moving these over, subtracting them, and then dividing that off, divided by 2 times 11 times 19. And that should be negative, actually. And that's a 0.54066. Roughly, cosine inverse of that means that B is equal to 57.27 degrees. And then I would repeat that with maybe a second anchor. Let's try this one with these three. So that would give me, I'll do this one in blue, sorry, 19 squared equals 11 squared plus 16 squared minus 2 times 11 times 16 times cosine of the angle between them. So cosine of A, subtracting those across, gives me 19 squared minus 11 squared minus 16 squared over negative 2 times 11 times 16, which is like a 0.04545 and so on, which means cosine inverse of that gives me 87.39 degrees. And I can figure out C by doing 180 minus 57.27 minus 87.39. For a 35.34 degrees. Which, you kind of think about it, it makes sense that you look at the smallest side, the smallest angle is going to be opposite it. The smallest angle is going to be, the largest angle is going to be opposite the biggest side, so 87.39 is the largest, and B is somewhere in between. Fabulous. All right, so now let's move on to an application. Oh, let me get rid of that. An application problem, or two, that involves those law of cosines, law of sines, and to solve those. Okay, we've got points A and B that are on opposite sides of a building, and the surveyor selects a third point to place a transit. So point C is 47 feet from A and 64 feet from B. So let's just say these are the two things that are on opposite sides of a building. This is A and this is B. We're going to put a C somewhere out here, and we know that this is point C is 47 feet from A, and this is 64 feet from B, and the angle ACB, which is right here, is 52 degrees. We want to know what's this side right here, and hopefully right away you see that's a law of cosines anchor. Because we can then set up the equation. Let's call that x. We know that x squared would be 47 squared plus 64 squared minus 2 times 47 times 64 times cosine of the angle between them, 52 degrees. Okay, throw that in the calculator. So x squared is 2,601.18. Take the square root of that, and I get 51.00, or 51 feet. That's how far apart A and B would have to be. All right, next problem. 13. The distance from home plate to dead center field at a certain baseball stadium is 408 feet. So remember this picture, which I always poorly draw, but we've got this distance out here to center field. That total length is 408 feet. The baseball diamond is square with the side being 90 feet. So this is also 90 feet over here. So we want to know how far, if I know this distance in red that I just drew is 408, and this distance in red here is 90, and of course this angle right here has to be 45 degrees because it's half of an angle of a square. We want to know how far is this. That's the question. And again, it's an side angle side problem, which is easily recognizable as the anchor. We know this, this, and this, boom, boom. So if I called that x, x squared would be 90 squared plus 408 squared. Try that again. Write that one more time. 408 squared minus 2 times 90 times 408 times cosine of 45. So x squared equals 1, 2, 2, 6, 3, 4. Take the square root of this, and we get 350 feet. I'll go ahead and throw in a 0.2 for just a little extra accuracy. 350.2 feet done for that particular stadium. Worth noting that different stadiums vary for the distance, so it's not a fixed number for all of baseball when you measure dead center to first base. All right, areas of triangle. There's two formulas that you've got to know to find the area of a triangle. K can either be 1/2 AB sine of the angle between two, or you can use the semi-perimeter formula, which is S minus A, S minus B, S minus C, where S is the semi-perimeter. Take the square root of that product. So this one, easy peasy. It is angle side angle, so you immediately can just say that K is 1/2 3 times 6 times sine of 25. 3 times 1/2. 1.5 times 6 is 9. Sine of 25 is 0.4226. So multiply that, and we get the area of this triangle would be 3.80 done. 15 would use the semi-perimeter formula. K equals the square root of S times S minus A, S minus B, and S minus C. And S is 1/2 A plus B plus C. So in our case, that's 1/2 9 plus 9 plus 7. 18 plus 7 is 25, so this is going to be giving me 12.5. If I do that, let me just double check by throwing in my calculator, 12.5. So now we get square root of 12.5. 12.5 minus 9. 12.5 minus 9, and 12.5 minus 7. So 12.5, and then times 3.5. Times another 3.5, times now a 5.5. And take the square root of that, and I get 29.02 is the area. And there we go. One last problem and we're done. Number 16. A painter needs to cover a triangular region that is 62, 69, and 73. And a can of paint covers 70 square meters. So we need to take and find the area, and if we divide that by 70, that will tell us the number of cans. Of course, we'll need to round up, because if we get a fraction of a can, we got to still use or buy the whole can. So let's use the semi-perimeter formula again. S minus A, S minus B, S minus C. So S is 1/2 62 plus 69 plus 73. 62 plus 69 is 131 plus 73 is 204 divided by 2. I get 102. Okay, so that means that K would be square root of 102 times 102 minus 62, 102 minus 69, and 102 minus 73. So 102 minus 62 is a 40. Multiply that. 102 minus 69 is 33. Oops, I got to start over. 102. Plugging it all in. 1975. Actually 76 when I round. So if I take K over 70, that's number of, or the area divided by 70 square meters per can. That will give me cans. 1976. I can't write, sorry. Divided by 70. And I get 28.2, which means I need 29 cans to cover the area of that triangle. And with that, we are done. Oops, sorry, let me go back.